Fred, Fred, your birthday celebration was a year ago, 2 years ago? A year ago. Oh, okay. And Alan told me his birthday was last week. Next week? Oh, I did not. Oh, I see. I see. Okay. Huh. He seems doing well. Still has the steam to go. Oh, that's a diffusion process. Right? You control. I just go. I just stay there. Ah. This email is fresh. 3:50 today, 10 minutes ago. 10.6. NREL. This is from NREL. Okay. This device. I probably will not mention, but we should celebrate. Really? So this is the Institute of Energy Efficient?
Yeah.
Good. Yeah, I had lunch with David Austin. He's good. He's good. Yeah. You guys could have someone to run this. You should have a good. Yeah. No problem. No problem. I think this is important. Yeah, you no choice. Yeah, it's a hard deadline. That's true. How old is he? Two. Okay, well, that's important.
Okay, while a few more people are getting their libations and food, I'd like to get us started. So today we have the unusual privilege to have among us one of the most, I will project the most cited scientist / engineer in organic electronics. And that would be Professor Yang from UCLA. And as of about a year or so, he is the, how did I get his name correctly? Carol and Lawrence Tanis Jr. Endowed Chair Professor at UCLA. Yang started as a scientist in Taiwan, and moved from there to University of Massachusetts Lowell, where he worked with Semiconductor, a physicist who in fact created the more successful company in organic solar cells, namely Organica. Unfortunately, Semiconductor succumbed to a swimming accident in Hawaii about 10 years ago.
11.
11 years ago. But from there, he went to Riverside, where he did a postdoc with another very famous chemical physicist, physical chemist, spectroscopist by the name of Fuller. So he seems to leave something behind him, because unfortunately Fuller is no longer with us. Succumbed to a brain tumor, very unfortunate, because he was a magnificent scientist, scholar. And from there he went to Uniac. Uniac succumbed to DuPont. So Uniac no longer exists, but it's a DuPont display. And from there he went to UCLA and went up very quickly to the ranks to the chair position at
It's good to come back. I never actually officially been at UC Santa Barbara, but I was in Santa Barbara at the time. I come to UC Santa Barbara often enough. I'm familiar with the campus. But today when I come back, I cannot recognize because there are so many new buildings and so many bicycles as well. So I was alert several times to be careful about the bicycle, but that's good. Anyway, before I start, let me introduce some of my co-authors. Mr. Dou, Le Tian Dou, is a very brilliant young chemist from PKU, Peking University. And Dr. Yu just sent me an email that he has just achieved a new record as a postdoc in our group from Chinese Academy of Science. Dr. Gang Li, formerly at Solomar, was their research director. He wanted to be a faculty, so he joined UCLA so to prepare his resume. I highly recommend him to any institute interested in this technology. And then, so anyway, the reason I'm pretty excited about this opportunity is because the heterojunction that we are talking about now is in fact start from Santa Barbara. It was actually invented when I was in Santa Barbara, when Sada Shifshi and Gang Yu was here, and so I had the privilege to personally involve in this, witness this invention. Anyway, so the way how it works is, in principle, actually, Fred can correct me, in principle, this idea should not work. Why? Because they mix all the PN junction together, and then it should cancel each other. But miraculously, the polymer has a tendency to form this nice bifacial, continuous phase that make it work. So if you think about if you have a PN junction in the front connection, left connection, you know, the orientation point to anywhere. So I think that probably should not work, as well as if you have the device, but the morphology, the junction are all sort of interconnected, interpenetrating network. So the bulk heterojunction has a very high interface area, efficient exciton dissociation, and charge transport. This is a major bottleneck. Actually, I talked to Professor Alan Higa today that we both agree that this will be the next thing that we should work on that. The phase separation is important, and the interpenetrating network, I mentioned to you, both donor and receptor. And the domain size should be about twice of the exciton diffusion length, about 20 nanometers. So this constructs the bulk heterojunction structure, the phase diagram. So let me give you a typical introduction of how this works. So when the photon comes in here, it excited, here's the yellow thing is a photon, excited the charge, electron and hole separate in the interface, and then collect subsequently by the contact electrodes. So it looks very simple, but in fact, the whole thing is quite a challenge to make it. You make it work, it's not difficult, but make it to a high efficiency is a lot of work. And I'd like to introduce the PCBM, which is the invention by Professor Fred Woodall. He is in charge of the meeting today. So the whole process is you have photon, you got the absorption, exciton diffusion, charge transfer, and then charge collections. So the important part is how to make the interface or the morphology the way it should be. I have to point it out, each material is different. And so there's no standard formulation to say this is the so-called SOP, standard operating procedure for the polymer solar cell. So for instance, the P3HT is a very commonly used semiconductor polymer that the way to make a device is different than other polymers. A year ago, Professor Fred Woodall celebrated his 70th birthday. So I came here, I gave a talk. I put this list here. This is all kinds of different high-performance polymer a year ago. And I pointed out this PCBM system that no matter how you change this polymer here, the PCBM remains the same. That's what we call classical materials. So still today cannot change it. So I think Fred should be very proud of that. But I want to point out one thing, that if you look at the performance, a year ago, 7%, 6% was considered, 7% here was considered to be high. How about today? So, okay, here's a molecule structure. I'm not trained as a chemist, although my professor and PhD advisor is in the chemistry department, so I really, so this is the chemical structure we actually just copied down from the papers. So what I'd like to your attention is one of these material that we will be talking about this today is this molecule PCBD TBT invented by Professor Heger's group and also Organica, and we actually modified by replacing the silicon atom to the carbon, so it's actually improved the performance a little bit. But I want to show you this chart. A year ago when I showed this chart, I said, look at this from 2006, 4.3% P3HD material, you go all the way up. And then it's hard to keep this momentum going like that in any field. We know that. So, but look, this is a time scale, 2011. Now it's 2011, end of 2011. Professor Yong-Sao report 8.37% efficiency, certified by an institute. And we report 8.62 efficiency certified by NREL. And here it is. We have, Yong-Sao has 9.2%. This is still before end of 2011. And then we have about 10% efficiency. This is unofficial because I put a star here. A star is uncertified. And NREL certified this number to be about 10%. So you can see this momentum does keep on going in a very nice way. So today is the first month of 2012. So I can see this trend still moving forward. So one hand of talking about a successful technology is one issue which we all enjoy that. But whether this technology will turn into a successful business and industry will be a separate issue I will discuss at the end of the talk. Okay, so this is our work. Briefly, I sort of drawing the chart here. So in fact, our research, solar cell research, started from 2001. And then we have published in this time about 70 papers, 70 on organic photovoltaic. It divides the amount of funding we get and then by the number of paper we publish. In fact, each paper is quite expensive. So I did a simple calculation. It's enough to buy a nice car. Okay. So I want to credit to a student which he's doing very well in Taiwan. At the data point here called Professor Fang Zhong Chen is in Chiao Tung University in Taiwan. Because in 2001, 6 months before the end of his PhD thesis, he said, Professor, I'd like to do something different. As Fred mentioned, we were working on LED at the time. I said, well, what do you want to work on? He said, I want to work on solar cell. I said, well, I don't know how to do it because I worked on polysilicon solar cell when I was a PhD student, but I never worked on polymer solar cell. So he says, that's okay. He liked to try an idea about using triplet molecule. He was working on triplet exciton for LED. So I said, how much money do you need? He said, I need $30,000, mainly to buy lamps, equipment, to set up the measurement. I said, go ahead. I found $30,000 for him. So after a while, the idea doesn't work, which is not surprising. You know, the graduate student, the idea need to be polished. But anyway, we took the idea. Eventually, we got something going. We wrote a nice paper. And more important, we wrote a proposal to UCEI called UC Energy Institute. It's University of California. And the student could be a co-PI on those particular proposals. I encourage all the students to try that. And we got $30,000 grant. So I gave him $30,000 by equipment. We recovered $30,000. From a business point of view, we break even. Okay. More importantly, one of the referees, I don't know who he is or she is, it says, I don't believe polymer solar cells. But I still strongly support this proposal. Sounds good. And just to prove my concept is wrong. This is the beauty of this country. I saw a lot of foreign students, probably from Asia. That is, I came from Taiwan, briefly introduce myself, that it's a place that if you feel successful, people like you, but you fail, people blame you. But in here, that is, people give you money to prove they were wrong. How can you find a better place like that? Okay, so I'd like to encourage you that not all the experiment or research work works, but anyway, the experience are worth to going on. I want to mention a particular paper that is, in 2005, we published a paper in Nature Materials controlling the morphology. We reached a 4.4% efficiency, and this paper is by Dr. Gang Li. And this paper, to the best of my knowledge, is the most cited Nature Material paper today. That it has been cited, I think, 1,800 times in 6 years. It's pretty exciting. Anyway, so we have reached 8.62% efficiency. Now this number should be rewritten about 10% now. Okay, so during the course, we have a new star company established about 30 miles inland. So this is called Solomon, established in 2006. So this is a company. And then currently, there are about 20 plus employees and doing similar things as Organica doing. So this company is actually quite visible compared to, I have a privilege of working with Professor Sukhan Tripathi. He started Organica, and then we start Solomon that as a friendly, I would call it a friendly competition, because we need more than one company to work on an industry to bring the technology to the market. Okay, so let me introduce some of the terms that I'll be talking about today. So this is the typical IV curve with the voltage and the current. Open circuit voltage is the data point here, short circuit current, and here the least square is called maximum power output. So you can have a short circuit current, open circuit voltage. Fill factor is the least square divided by the square. I'm drawing sort of manually by the laser point. So this is called, if you have a power conversion efficiency, PCE, we listen to this quite often, is defined by the maximum power square divided by the outside square, which is equivalent to fill factor times ISC VOC divided by incident of light. This is a sunlight, which is about 1,000 watt per meter square. So this is quite an easy number to remember. So this is the definition of the power conversion efficiency. So what I'd like to mention about, we already talked about the single layer structure, how this thing can be done. So they have, Professor Yonsa has reached 9%, and the Mitsubishi Chemical is a Japanese company, recently certified 10.1% efficiency. And then there's very respectable number. But their industry, they don't want to tell us how do they make devices, and nor they don't want to tell us what kind of material we use. At university, our job is to spread the knowledge. So later you will see our molecular structure, you will see our device structure. So our hope is the knowledge we generate will be beneficial to the society, so you can, based on knowledge, you can continue to push the technology forward. Anyway, now we talk about tandem solar cell. What's wrong with single layer? Nothing wrong with that, if you can make it work. The problem is, here's a solar spectrum. The beauty of, or the part of the problem of polymer, or maybe unless you make a copolymer, that is, the absorption window is pretty narrow. That's why our eye, which is the molecule to pick up the photons, you can see visible. You can move this absorption peak to more infrared because you can pick up more photons. However, the absorption window is still there. And the other possibility is, okay, how about we can mix two materials together? But the problem of that is VOC. If you remember the equation of the efficiency, is not just current. It's open circuit voltage also play a role. So one can move this absorption more into infrared. But here's what we call the bandgap. Your open circuit voltage will be subject to the bandgap. The smaller the bandgap you have, the smaller the open circuit voltage you have. And then the absorption will not necessarily help you that much. So the solution is to have a structure, have a tandem solar cell. So the tandem solar cell is very simple. You simply put two materials, say the red one and the green one, connect together, and then you overlap a major portion of the solar spectrum. In the meantime, you don't waste the photon because you have the open circuit voltage here. Open circuit voltage, you can add up these two things. So just think about two batteries. You have 1.5 battery, bulb battery, and then the other one is 1.5. You got a 3 volts output. So that's the beauty of the tandem solar cell. So what is the price we have to pay for it? It's hard to make. It's not easy to make. Professor Higa in 2007, I believe, published a paper in the Science about the tandem solar cell. And the key issue is here is the interconnecting layer. How can we build a junction to connect these two cells together? So today, there's a company called Spectral Lab, located about 30 miles north of UCLA. It's a Boeing company. They make about 42% triple junction solar cell. It's a very respectable company. They build solar cells for space, for satellite. And then we actually talk to them from time to time. They teach us how to make our solar cells. The trick is here. How can we build a tunnel junction such that the electron from one cell, the hole from the other cell will recombine in this tunnel junction? That's the key. So without saying that too much, so here's what we are going to do is the working mechanism of the interconnecting layer. So a photon comes in, and then the electron hole pair will go to the interconnecting layer, which are showing here, and recombine. And then the leftover electron and holes will be collected by the electrode. So the VOC will add up. The JSC, on the other hand, will be, the VOC will add up, JSC will remain the same. So the key issue is make a JSC, the short circuit current, identical in the front and rear, because you will go with a smaller one. You can make one cell extremely efficient, and you can make the other cell extremely inefficient. Unfortunately, you go the inefficient ones. So that's the key. Okay. So the interconnecting layer must be optically transparent. You don't want to pay any toll in this interconnecting layer. It must be electrical conductive and physically robust. Why is it important robust? Because we are using solution process. Every layer we talk about today will be solution process coated, except the electrode. So that's why you need to be physically robust. And then here's a regular structure that we define ITO as the positive contact, and this is inverted structure. ITO is the negative contact. So in principle, a regular structure are the current structure a lot of people publish, but the inverse structure, in fact, to the best of my knowledge, are those structures the industry use to produce their solar cells because it's more stable. Oops, not working. Okay, so this is our regular tandem solar cell. This structure is actually rather similar to what Professor Heger published in a science paper. So let me start from the bottom. We have a glass and ITO substrate. We get the P dot is a conducting polymer, and then this is a PHT PC70BM. This is the active layer, the first active layer. So this is the green IV curve is the first solar cell. And the interconnecting layer is a TiO2, titanium oxide processed by Sojio process, and the P dot. And then this is the PSB TBT. Remember I showed you the structure with the silicon here? So that's the second layer, and then the TiO2 doped with the cysteine carbonate on the top, and then metal electrode. So this, you can see the IV curve. This paper published in 2010. We got the 5.9% efficiency. So I want to show you this VOC. If you add these two numbers, you get 1.27, but we get 1.25. We are very close to the theoretical number, so it indicates we really do a good job here. But if you look at the JSC, with the black curve we have still much lower than the green curve is supposed to be. So indicate even the VOC adds up, but the conductivity of the middle layer is still not there. We need better conductive materials, maybe another N-type semiconductor rather than TiO2 is more or less like an insulator or photoconductor. The field factor is not bad. The 63% is not bad. So we published in 2010. The reason I want to point out the year is I want to show you how fast this area has been progressive. And this paper we just recently published in 2011 by Jun Yang. He's currently working in Solomon now. So you can see that the green curve is still the P3HT. The red curve is the PSB TBT. This is still the materials. We improved the interconnecting layer. We also used ICBA, which is a new PCBN derivative. Was patented by Plestronics, but was reported in the scientific paper by Professor Yongfang Li from Chinese Academy of Science. So you can see we reached about 7% efficiency in the paper in Advanced Material in 2011. So that trick is to raise the open circuit voltage. So let's go back to the one. You see the open circuit voltage is 1.25. We reached to 1.47. So that's why you improve the efficiency to about 7%. So just to give you a flavor how to capture the photon and then how to turn the photon into useful energy. We also found that the device under 1 sun and 6%, and then when the 0.1 sun, you can reach about almost 8%. So it means indicate this technology is actually might be useful. I use the word might be useful for indoor in the future. So not necessarily all the solar cell has to be outdoor. So some of them can be indoor to recapture the photons. I was once sitting in an airplane, and then the passenger next to me, I start to talk to him not long since the airplane took off. And then we were exchanging ideas, and then I asked him, what do you do for a living? You think about that, you say, I design. I said, what do you design? And he pointed out the LAX, they're building a new terminal. He told me I designed that. I said, really? And what else did you design? And then he said, have you been to Korea? I said, I've been to Incheon Airport. He said, I designed the Incheon Airport. I said, oh, wow, that's very impressive. So I started asking him a business card. Okay, anyway. So I started talking to him about this type of solar cell indoor lighting. And then he said, that's great. Maybe we can do something in the airport. They bring in a lot of light from outside. So they need to different colors decorated internal of the airport. So that could be something that the architect design can utilize that. So anyway, so that was actually a pleasant trip to know such wonderful person. Okay, so interconnecting layer, I talk about TiO2 is not easy to handle. I'd like to tell you why. Because for the TiO2 is a photoconductor. So if you just build a solar cell, this is a dark curve. And the student might measure the IV curve and walk away and say that this idea doesn't work. But I want you to be patient because you need to a little bit UV light as a trigger to have a photoconductivity. So you can see the IV curve without light soaking and with light soaking. You get a very nice IV curve. So that's the trick. So I want you to be careful, particularly graduate student, that if experiment doesn't work, go get a cup of coffee, come back, your experiment might work. Okay, so again, you need to be patient to give it a little bit time, so this thing will start to work. Okay, so band structure. For physics, the band structure is probably the most important thing in all this structure we're talking about here. So you can see the P3H, this is a regular structure I want your attention, P3HT, PCBM. So P-type, N-type. N-type electron will come to TiO2. You can see that after photoexcitation, that the band bending, and then so before the photoexcitation, before the UV light exposure, and after UV light exposure, you can see how the band diagram changes. The band start to bend significantly, the tunneling can happen. So the tunneling penetrate, the electron penetrate from the TiO2 to P dot, and then P dot, it's not a very clean material. It's good for the charge recombination. So that's why it's a tunnel junction happens. If you go and look how the spectral lab designed the Tandem solar cell, that's exactly what they do. Not the TiO2, but they have a heavily doped N-type here, heavily doped P-type. So the two heavily doped, the band bending, so you form a tunnel junction there. So that's a trick of the building a good Tandem solar cells. So let's start with, we have to build a little bit better Tandem solar cell. So about 2 years ago, or maybe a little bit more than 2 years, we start to build this called inverted polymer solar cell with an inverted polymer Tandem solar cell. So why do we do inverted? We can avoid the P dot potentially, but we still use them. Solution process, the metal oxide interconnecting layer is easier to handle and reproducible. And the anti-metal oxide based on the cathode for better stability. So we don't have to use calcium. You probably noticed some of my devices using calcium, which is not the most reliable material you want to use. So let me give you an example. You want to build good Tandem solar cells, you have to start to build a good single layer device. So this is what we did. ITO, instead of P dot, we use cesium carbonate. Here, CS2CO3. So this is a yellow color. And then this is a PCBM, P3HT, everything inverted. The calcium, this is a regular structure. We don't use calcium, we use B2O5. So this paper we published 2006 by Dr. Gang Li turned out to be the first inverted polymer solar cell publication. And then later, NREL and then Organica all follow the same trend, which I believe that they came out with the idea independently because the publication they are very close. This thing doesn't work. Okay, so slowly we make our solar single layer invert structure better. So we are able to do this. You can see that in 2008 we reached about 4.2% efficiency by building better device. Major is in the interface improvement. We spend a lot of time of working on the metal oxide layers, and turn out to be able to credit to Judy Park. Judy Park is a Korean student in my group, and her husband is working with Professor Brucedown's group. If you know Professor Brucedown, he's an expert in metal oxide. So when husband and wife work together, you see how powerful the combination is. So that's how we continue to improve our device. And of course, we appreciate the input from her husband very much. Her husband is expert in the Sojio process. So keep on improving that. And then about a year ago, we start to introduce metal oxide into the interconnecting layer. This MO3 at that time was somewhat evaporate. Aluminum is a somewhat evaporate. Zinc oxide is solution process. But today, we're able to do all of these layers by a solution process. We don't use aluminum anymore. We just take it out. MO3 and the zinc oxide Sojio process. So we're able to build these solar cells in the inverse structure, and very useful. So if you take this old data, you can see that we do the cross-sectional SEM. We can see that the crystal structure of the zinc oxide and then the ammonium oxide, and then the very thin aluminum layer. The purpose at the time of aluminum layer was to introduce extra carriers, sort of a doping process to dope the zinc oxide and MO3 to have a higher carrier concentration. It turns out to be a very thin layer of aluminum is exactly what Spectral Lab used for their tunnel junction. They put a very thin layer there as a dopant for their tunnel junction. So this is a sort of a drawing of the connecting of the two battery together. You can see the two diode with a metal wire, but this metal wire must be transparent. So that's the trick. So how do we do here? Pretty good. We are able to build this inverted device. You can see that the current of our inverted device are able to catch up with a smaller current here. So the way to improve it is reduce the current here by reducing the thickness. By reducing the thickness, the front cell, the back cell will improve it, and the overall will be improved. So that's the beauty of if you are able to look the EQE, external quantum efficiency curve. If you look at these two blue curves, it's called light bias. This two is P3HT and the PSB-TBT. You can see that the ideal scenario is you want to have the product of these two curves, the integral of these two curves to come out to be the same. At this moment, at least one is not the same. One is still higher than the other one. So, and in addition to that, you can see that there is substantial overlap here. This overlap means that P3HT is taken away the photon from the PSB-TBT. So the ideal scenario is that can we move this polymer a little bit further away from P3HT, that there is less overlap. With less overlap, then it's better for both parties. So that's what we were doing. So this paper, I believe, it's probably 2010, is we have the power conversion efficiency about 5.1% of the optimized tandem solar cell is a PSB-TBT. Okay. So if you look at the band structure still that we use moly, aluminum, and zinc oxide at the time, and then the aluminum behaves as a Fermi level to pin the PN junction there, and then this tunnel junction, it should not be a PN junction. PN junction, then you're in trouble. So you can see the front cell and the back cell, and then the interconnecting layers. So the interconnecting layers, this is absorption. You can see how transparent this is, a transmission, almost 100% cross the absorption of the solar cell. So this is sort of the criteria of the interconnecting layer from the physics point of view. So if you look at the time scale, this is about a year ago. So my student, Le Tian, he finished his prelim exam. He started about a year and a half ago. And he asked me, Professor, what is my research project? I said, very simple. Make an infrared polymer. He said, why get broader absorption? I said, no, I want you to make a narrow absorption, but infrared, absorbing infrared. The reason is very simple, because this guy is too broad. If I can narrow it down and can push this one a little bit to the right, then that would be an ideal tandem polymer. So that's what he did. He spent a year of designing a new polymer. And so actually, let me come back to these slides. So this is the material, PBDTT DPP. So a new material that we designed, and this is frankly speaking, this is the first time we actually present this material to the public. And so we use, this is our acceptor PC70BM and ICBA, and then this is a front cell P3HT. So let's go back to the cell structure. We have ITO glass and the zinc oxide solution process. P3HT ICBA is the front cell. P dot, PS, we still use P dot, just have to live with it for a while. And zinc oxide, solution process zinc oxide. And the low bandgap polymer is the material I just described, PBD, TT, and DPP. And then moly oxide and the silver. So everything from here to the top, solution process, except the silver electrode. We still have to do the thermal evaporation. So from the manufacturer point of view, if one can do all the solution process, that would be tremendous, simplify the process. Okay, so I have to speed up a little bit. Okay, so this is absorption. So this is a nice material that we are using, and then this is P3HT, our good friend. So you can see it covers nice solar spectrum. 1.4 for EV, the other one is 1.9. Okay, this some of the characterization. This is a CV, cyclophotometry curve, and then this is SC, space charge limit current. To measure the mobility is about 10 to minus 4. This is quite respectable. It's not perfect, but if 10 to minus 3 would be even better. Okay, that's what the P3HT is about. So we have mixed with the PCVM and then this broad spectra is. So regular single layer device, inverted single layer device. These two devices come out to be almost identical. So the low bandgap polymer owns a high mobility, low homo level, and the base device, single junction device shows about 6.5% power conversion efficiency. So how about Tandem? So this is the device we sent to NREL before Christmas. I would appreciate, I need to mention Tom Moriarty and Keith Emery. They actually come back between Christmas and New Year to finish our measurement for us. You can probably see the late date. They probably have a date. Okay, anyway. So we come out to be about 8.6% efficiency certified by NREL. So we have a natural photonic paper. So this paper is in press. It's being accepted. I don't know when it will be published. So this is the IPC or quantum efficiency curve that you can see that this is nice narrow absorption. It would be nice if we can push this one a little bit further to infrared. Maybe that's Fred can assign one of his students to do that. I'm happy to do the testing for you. So this is the two curves. But if you look at that, this is about 65%. This is about 48%. So we still have a room to improve. We can make this one a little bit smaller and make this one higher just to balance the current. This device is extremely stable. We encapsulate, but this is in air. Protect by simple epoxy. In air for about a month, we don't see any decay. Virtually, it's very stable. That's why we can send it to NREL. They play around. They can do all the testing. Okay. So this is a recent new material. Not the material compared to the one we synthesized is different. So this is a new material that we have measured at UCLA about 10.2% efficiency. And then, so this is the 8.62 the NREL 35. This is measured in our lab about 10.2 efficiency percent. I have to tell you that NREL measured it, and then I just got another email from my student, my postdoc, 10 minutes before I gave the talk. I showed the email to Fred. Actually, NREL did measure the device, but they have not certified yet, so I should save it. I can tell you it's in the double-digit range, and is probably highest among all the report numbers. But at this moment, I think I should save it until NREL give me the chart. When NREL provide this chart, it's called NREL certified with their logo, then I can talk more publicly. But I think this is good news. Important news, why is that? Because we are in the double-digit 10% or above range, then we should move into next milestone. Okay, so a summary that briefly, I have another topic to give, but that one can go faster. We have demonstrated a high-performance tandem solar cell investing in interconnecting layer working mechanism. We demonstrate low bandgap polymer BBDTT DPP specifically designed for tandem solar cells. To the best of knowledge, this is probably the first molecule that people designed for the tandem structure. The significance of this polymer is clearly demonstrated in the inverted tandem solar cell with 8.62% efficiency measured by NREL. And finally, a new, should be low, not low, LOS. Bandgap polymer pushes our tandem solar to reach about record 10% power conversion efficiency. So this is about the tandem solar cell. So the remaining about 5 to 7 minutes, I'm going to tell you another nice concept that we're developing in our lab that is called polarizing organic photovoltaics. So this has to do with iPhone or any phone. If you look at the phone, the display looks black. Why it looks black? It's because there's polarizers. In order to have a liquid crystal display to work, you must have 2 pieces of polarizer to cross out the light. And unfortunately, these 2 pieces of the polarizer pick up most of the photons. So I will talk about the mechanism later, but let me introduce Dr. Zhu and Kikuma now currently in Intel. So Dr. Zhu, I highlighted the name Z, so I explained to you why I do that. Anyway, so liquid crystal display is very popular display in everywhere, except a few smartphones has OLED display. Most of them are liquid crystal displays. It's very power hungry because the reason I mentioned to you earlier. So you see the backlight coming out, there are 2 pieces of polarizers killed at least 50% of the light, if not more. So the liquid crystal in between behave as a light bulb, you switch the photons. So how can we, so this is the polarizer. You can see if you cross 2 pieces of polarizer, you can more or less complete. In principle, you can completely cross out the light. So you pick up all the lights. But the liquid crystal molecule in between, which showing earlier, this liquid crystal molecule can twist the light to the, if you need the pixel to be turned on. Okay, so the energy, more than 50% backlight energy is wasted in the polarizer. In fact, 5% of light from the backlight are seen by the eyes. You see those photons, they're only 5% from the backlight. The 95% disappear somewhere in the process. So I was invited by Intel along with another about 12 groups to present, not present, but to Intel say, we want to solve this problem of the energy efficiency display. So we proposed this idea to Intel, and then it actually works. So what we have done here is that we use the PCHT, oriented PCHT, as to replace the polarizer. Not very good at this moment, but we demonstrate prove the concept. So so we want to use the molecule, the polymer, to do the orientation. In fact, this idea of the oriented polymer was not new. When I was at UNIX, the time Postmates and Professor Heger and Professor Udo has demonstrated using the MEH PPV. Is another important invention by Fred, that they use the polystyrene to stretch the polymer to study the photophysics of the polymer. So instead of doing that, we actually using the mechanical rubbering to do that. It's not very good, but we should be able to find a better way. So the requirement for the photovoltaic polarizer is a high dipole ratio, efficient PV performance, and the electrode with good transmittance. So there is a commercial polarizer, just for your reference point. You take a commercial polarizer, the dipole ratio is the parallel and perpendicular ratio is about 80. Okay, and then this is absorption of the polarizer. You can see they nicely covered visible. So the technology choice is if you choose inorganic, organic, I can tell you inorganic doesn't work, unfortunately, or fortunately for organic. So this must be a unique application for OPV. Then this is a device architecture. You got a transparent conductor. Anyway, so this is our idea of the device. Transparent conductor, top and bottom, and then the active layer oriented, stretched polymer. So the unique feature of the organic molecule alignment gives an isotropic effect. So we named this polarizing organic photovoltaics. Instead of if I use POPV, people will think it is a polymer organic photovoltaic. So I told my postdoc, I said, let's name it ZOPV. And then because his name is Dr. Zhu, start from Z, so So that's giving the motivation to work day and night in the lab to say, okay, I'm working on the technology carried by name. So that's nicely done. So this is ZOPV stands for polarizing organic photovoltaics, and Dr. Zhu is very happy I named this device his name. Okay, so the trick is how can we orient the molecule like that? And actually, Professor Udo probably a better person, or Professor Postmith in this case, better person to do that. So what we have done here is that we take a P3HT, spin coat the film, we take a velvet cloth, we heat up the film, we rub it. We actually have the Facebook click. If you want to see it, send an email to me. I'm happy to show that to you. And then that's orientation of polymer. And then you can see the dichrome ratio we achieve about 16. It's not perfect. It's not 80. But 15 or 16 is not bad either. So we're able to polarize the film. You can see this is a piece of polarizer. And then this is parallel to the polarizer. This is a perpendicular to the polarizer, one way or the other. Yeah, this is a perpendicular, this is a parallel. In fact, if you look at the latest issue of a Science magazine, you can see this article with these pictures there. Okay, so so this is the famous UCLA Loris horn. It works. How about the device? Oops. So forming independent, remember, we need a donor acceptor. So we talk about only the donor. How about the acceptor? So the acceptor was bringing in, and my time's up, and then the diffuse. Professor Ben Shorts at UCLA, they actually work on the bilayer device structure. Later turned out to be the bilayer structure is not so bilayer. The PCBM actually diffuse into it. But this is exactly what we want. We want to orient the polymer film, and we want the PCBM to diffuse it. So that's why after we rub the P3HT, the PCBM diffuse into it. Nicely well done. So Ben was very happy because at least his invention has some useful to, not necessarily to the device, but at least to prove the disoriented solar cell. So we saw quasi-bilayer interpenetrating network. So okay, the device, we're able to reach the current. You see the astral peak has a different current. So the efficiency is about 1.25% efficient. Under the transparent electrode, if we put a non-transparent electrode, it reaches about 3%. It's not bad. Okay, so the ratio is about 3.5. It's okay. So the future challenge is highly transparent electrode. We are working on that. Efficient film orientation process. That's why I come in here talk to also Professor Ed Kramer that to see whether he has any magic that can help us to do this orientation. And then we probably need the new OPV materials, easy to align to achieve a high dichrome ratio and a high PV performance to achieve high electricity production. Finally, I'd like to answer a question. Most people like to ask, I present this slide different places, but I will finish in 2 minutes. Is OPV a real technology or just published paper? Personally, because I involve, there are many issues we need to solve. If you want to list all the problems, you need about 3 slides. Okay, now, Fred mentioned to me about organic LED I work on. I joined UNIX in about 1992, 93. At that time, it was a terrible device, only a few hours lifetime, efficiency was less than 10 lumen per watt. And currently, OLED has about 50K to 100K hour lifetime, 50 lumen per watt efficiency. And Samsung announced, and they are doing that OLED will be their next generation display technology. So we talk about this nice Samsung phone. If you look at the display quality, it's really fantastic. If OLED can do it, how about OPV? I think I'm quite confident this can be done. But it takes time. You know, it's not just dumping the money, but also takes time. So we want, I prepared that the 10% barrier will be in 1 to 2 years. Now 10% barrier is no longer a barrier, we're on 10%. We'd like to reach 15%. This will lead to about 10 to 12% panel efficiency. So this is significant to the renewable energy, since OPV panel can be printed like a newspaper. Hopefully it can be printed. It certainly can be printed. I hope the industry and manufacturer can kick in to help us. You know, this is the Thai industry should think about to participate. That's how Samsung got involved. It started from about year 2000. They start to work on the OLED manufacture. Not easy, not trivial, but doable. I'd like to thank my people. This is my group. This is Judy, and this is our group that working on the project. This is Mr. Le Tian Do, the first author here. Dr. He now went to ONRL, Oak Ridge National Lab. Dr. Murase is from Torrey, our visiting scientist. and Mr. It should be Dr. Junyoung in Solomon, and Mr. Tom Moriarty and Dr. Keith Emery at NREL to help us to certify that. Our funding of ONR, Air Force, Solomon, and NSF. Thank you very much for your attention. Yes, I'm not running away.
So practical question.
No problem.
Samsung, as I understand it, the OLEDs are going to be small molecule.
Right.
And once they come into being, you won't need the polarizers.
That's actually okay.
You're kind of operating against the moving parts.
Good. If you look at the OLED display, they still use polarizers to enhance the contrast. But the polarizer is so-called circular polarizer. So now question is, I have a question for you. How can I make a polymer as a circular polarizer rather than linear polarizer?
Make it chiral.
That's true. Good point. Yes. So that's still ideal there. Yeah.
I have a brief question. So when you look at the tandem cell and you look at the composite performance and then you look at the front and the back, so you manufacture those independently and exactly the same contacts?
Very good question. In fact, we built a, let me repeat the question so people can hear that. The question is, you have two single cells. So when we build the tandem, do we just use the identical condition, same contact? Am I correct?
Yeah.
More or less. No, the tandem solar cell, before you do the tandem, you want to make sure the material is correct. So we build very efficient single layer device. But tandem, on the other hand, is the car, you have front wheel, you have the rear wheel, you want to make sure those wheels are running simultaneously, smoothly. So you have to adjust the front cell and the back cell such that they reach the maximum current match. That's the trick. You don't want the one cell extremely powerful, efficient, the other one is not so good. So you want to balance these two cells. That's the balancing part. So the contact will be different.
But you might expect actually in the tandem cells that each particular component behaves differently from just looking at it individually.
So you have to, way to do it is, one chart I show is light bias IPCE curve or external quantum efficiency. You want to use a light bias to make sure these two cells behave more or less consistent. Okay, so that's the trick. Is when one build a tandem solar cell, how can you tell the behavior of individual cell without additional wire to the middle? Yeah.
So how do you do that?
You have a light bias. Say you have two tandems, two cells stacking together. So if you just shine light to P3HT, the other one would be like insulator. So you have to have a biased light to make this one like a short circuit the cell, and then you measure only one cell. So you have a light bias to, so that's a trick. That's the hard part because that's why we went to NREL to do it. And you know the certification for one cell is take about 1 day. It's a lot of time consuming for them to do it for us. I would really appreciate that.
Can you speak a little louder?
Yeah. Yes, it's important, yes. Okay, let me repeat your question. The question is, I had a conversation with Professor Heger that this morning we all agree that high mobility or transport property is critical to a solar cell. And the question is why the carrier mobility is important. It's very simple. Solar cell is the device generate the photons, from photons to electrons. And electron somehow has to collect by electron. So the electron, the faster the electron being swept or collect by the electron, the better it is before it disappears. We are competing a mechanism called recombination. And then the recombination is subject to the defects, either structural defect, electronic defect, or chemical defects. So the way to think about that is the faster you can take the charge out of your cell, the better you are. So very simple. So that's why you want the high mobility. Right. All of them at once.
So just a very brief follow-up to that question. So we're all used to these big numbers in FET.
Yes.
What is the highest space charge limit current mobility
Well,
is out there?
for the actual device, you can get one. You can get or one. You can get one for some material, but the problem is, will those high mobility also give you the proper absorption and also the proper diode? Remember, it's not just current; it's also the voltage. And then so the important part, if every parameter is fixed, then work on the mobility. But if you start from scratch, then you have to think about how can I meet all the requirements, the bandgap, the carrier mobility, the absorption, the high density of states of the pick up the photons, all these things you have to. It's not trivial, That's why I take my student 1 year to make one material. But think about that. If you make one material works, how many material he makes fails? That's a lot. Mm-hmm. Right. Okay, let me repeat this. So the video tape. The question is, do we do the parallel connection or serial connection to see the performance improvement? Am I correct? More or less. So the issue is actually rather simple. That is, parallel connection is. We also work on parallel connections. So that's one of the approach we're working on. But it's easier to just build a vertical connection, easier to do it. Parallel is a little bit difficult. But we published a paper recently using a so-called three-terminal structure. We're still doing stacking, but we wire one out. So we do the parallel connection. The beauty of that, you don't have to match current. You can have any current you want, and you just add the current. Yeah. And the VOC of polymer solar cell is more or less like a 0.6, 0.7 volts. They are typical standard. So that works as well. We are open-minded to anything. Okay, let me repeat the question. The front cell, at least on our slide, is always P3HT. And then the question is, do we look into other systems that have wide bandgap polymer but also a large VOC? The answer is yes. We're open-minded to all the possible. See, if you have any good stuff, send it to us. We're happy to collaborate with anyone. Yeah, and we are actually pretty good in predicting that. I did not mention one thing, that is my optical model. We work sort of blindly. Not blindly. That we sort of behind the scene. We do the optical simulation to make sure the photon distribution are evenly. To do that, that's collaborate with Yamagata University. Yeah.
I have a question about the tandem dioxide for the interconnecting layer. So can you explain further why it's not good enough for the interconnecting layer? And can we play around with the, nanoparticle size or things to improve it?
Mm-hmm.
That is an intrinsic property.
Okay, let me repeat what you said. Your question is TiO2, titanium oxide, why is good or why is not good, and how can we handle it? To be honest with you, I'm not the right person to answer it because I'm counting on my student to work on the TiO2 Sojio process. My best knowledge is this is not a trivial process, but it's a processing issue. So how you process that? So we actually has come out some formulation to do that. and but it's not easy to handle it. If we lost, if we synthesize a new batch of TiO2, we have to take about 2 weeks to find out the condition that we can handle it. So it's not always very highly reproducible. But once we make it, we make a big batch, then we can use it for a long time. Then it's reproducible. Yeah. Yeah, more about processing.
Okay, I think I'm going to stop the discussion.
Thank you.
Anybody has-
Thank you very much.